Koriolismsu, and this is a joint work with Anastasia Kizil. I'm from Department of Mathematics of the University of Manchester. First of all, I want to say thank you for organizers to inviting me here, and I hope I will entertain you with some of my research. So the outline of my talk is as follows. Since I'm a new member of UKAN, I will spend some time saying words about myself. Then I will give a short review on my research, and then we will get to the main topic, embedding in acoustics. I suppose not many people know what is embedding, so I will briefly introduce the idea, then say what we did about this idea, and if we make till here, I will show you some new results in wave theory, as I believe. And okay, so let's start. In 2012, I graduated from Moscow State University from the theoretical department of the physical faculty. Then I started my PhD in acoustics, where I was under supervision of Andrey Shanin, and this is the person who taught me everything, so he is the one who defined my way in this area. Then also some important parts of my life, I was in a long collaboration with Michelin, where I was doing some experimental work and mostly studying tire noise. And for a year, I worked as acoustical engineer on Huawei, mostly on acoustical design of car interiors. And finally, in 2023, I joined the mathematical department of the University of Manchester, where I work with Anastasia Kizil, and this work was mostly done with Anastasia Kizil. Now I will talk to you about some results I obtained in the recent 6-7 years, just for you to know what are my research interests. And the first one is quite a very well-known problem, a problem of diffraction by a circular cone. We know that we can say that this problem is still unsolved. However, there is a lot of results for here, and there is a lot of advancement. But in general case, we still have problems with it. And I considered one special case of this problem when we have a narrow cone and we have a paraxial field, a paraxial or incoming wave approaching the cone. In this case, we can use a parabolic approximation, and instead of wave equation or Helmholtz equation in stationary case, we can consider just a very simple one-way propagation process, and we suppose that all diffraction angles are small. And for this problem, you can obtain a very neat solution in the following, in the terms of the following integral. And the part I'm proud of that we not only obtained a solution, but we made an experiment and acoustically measured the field diffracted by a cone, and this field was coherent with the theoretical formula. So here is our experimental setup. We had a piezoelectric sound source, it was around 40 kilohertz, so it's like a close ultrasound. And then we had this cold cone we made from aluminum. And we used a Brüliker microphone, more or less standard. It's 1/8 of inch to measure the field. And it worked more or less well. And here are the results. So they are more or less in agreement with the theory. Here we have some oscillations close to the surface of the cone as we get far away from a cone. And here how the field behaves if we move it towards the vertex deeper along the surface of the cone. So here it's at some point it just start to behave as Neumann boundary. Another problem also in acoustic that I was doing with Michelin is to measure the oscillations of a tire surface by acoustic holography method. So here I have like an antenna consisting of 1,000 microphones roughly. And by measuring the sound field on this antenna, I was trying to reconstruct the field on the surface of the tire. Surprisingly, or not surprisingly, this is a very difficult problem to solve. And like one more or less standard technique is to use so-called Tikhonov regularization method. So this is an inverse problem. It's ill-posed. And even with this mesh of 1,000 microphone antenna, it's very hard to get decent solutions. But still, we were able to make it work in some more or less simple situations. Another thing I done also with tires or without the tires, and I think it's a universal acoustic measurement technique that everybody should be aware of. It's a method of maximum length sequence. So what I do is basically visualize how the waves propagate. So I have a point source, and by applying this technique, I measure the impulse response of the system. So here is the example of the response for this tire. I have a direct wave, the wave just directly reaching the microphone on the tire, a reflected wave here, and the edge wave, or like a couple of edge waves that go first to this edge and then to the microphone. And like the main thing here is to build a monopole source. So here is a model we built from a plywood. You have a driver here. Here is just a waveguide concentrator part, but here you have a piece of tube, which the geometry of which you know, just a circular piece of tube. And here with two microphones, we are able to measure the volume velocity produced at the open end of this tube. And then by calibrating the experimental setup, the source with this volume velocity, we were able to treat it as a monopole source and get all these results. And also, I have some results in medical acoustics, also quite practical ones. As you probably know, a human body has two circulatory systems. So we have our cardiovascular system. It consists of two circuits. And why it's quite simple to measure the pressure in the heart circuit, in the arterial pressure, it can be very hard to measure pulmonary pressure because this circuit is deep inside in our body and there is no direct way to access it. And we were trying to build a simple technique, more or less, to measure this pressure from the acoustic signals produced by heart. So there is two valves in the heart, and if the pressure is high, they close in different moments, and then by the difference between time of closure, they produce different sounds, and we can analyze the sounds and to judge, at least roughly, about the pulmonary pressure. And of course, this can be important for treatment of patients. And we also designed a device that does the whole process. Okay. But mainly, my main part of research, so here I was talking about like acoustical experiment and very practical things, but mainly I consider myself as a specialist in the theory of diffraction. And one problem that I want to tackle in collaboration with Rafael Lussier and Andrey Shainin is the problem of diffraction by a quarter plane. This is quite simple problem by statement. So the statement is simple. We have a hard half plane, a quarter plane. We have a hard quarter plane in a 3D space. We have a plane wave, and we need to measure a diffracted field, to find a diffracted field. And everywhere the field satisfies Helmholtz equation. It turns out that this problem is extremely difficult, but quite recently we were able to get some results for it. And like one of the results that you can present wave components as certain 2D Fourier integrals, and then by deforming these integrals along the singularities. And here you need to have in mind that since the integral is 2D, your singularities is also a 2D sets in 4D complex space. So the aim is to deform a surface, a 2D surface, in a 4-dimensional space. And that's why all the stuff is quite complicated, but at least from a computational point of view, we have some advancements. And another thing also related to the theory of diffraction, and also I think very interesting and important one, is the study of discrete diffraction problems. So one can approximate the Helmholtz equation by the simplest finite element stencil, just 5 points, finite difference stencil. And one way, of course, is to solve this problem is just solve it numerically, truncate the system, and then just invert the matrix. But we looked at this problem from a different perspective. We tried to approach it analytically. And it seems that you can extend a lot of known result from continuous case for this discrete problem. And one extension we built, we applied so-called method of plane wave decomposition, or built a Sommerfeld integral for this problem. So basically, we have an integral of such kind where this thing acts as a plane wave ansatz. This thing acts as a Sommerfeld transformant, something that you need to build or in order to solve the problem. And this is a differential form we integrate along. And why do I have a differential form or instead of differential? It's because in the discrete setting, I need to integrate along the surface of a torus. So my dispersion surface, the surface along which I put my contour, it's a torus. It's topologically different, and all mathematics is slightly different for this lattice problem. But still, for example, the problem of diffraction by a right angle edge in the discrete case, we were able to solve completely and find out a very simple expression or in terms of algebraic functions. Okay, finally, I think we're getting to the main topic of our talk. I still have plenty of time. And today I want to talk about embedding. And the idea of embedding is very magic. I think this idea is overlooked by many researchers, but I'm pretty sure that everybody should be aware of it. So what do I consider in general? I have some 2D diffraction problem of diffraction of a plane wave by a polygon. So I have some edges and some straight lines are connecting these edges. And instead of solving this problem, I starting to do tricks. I applying a differential operator to the field. And first of all, I choose an operator that commutes with Helmholtz operator. So it's basically any differential operator. Then I need to choose it in a way that it preserves boundary condition. And most importantly, it should kill the incident wave. And in this sense, because the problem is stated or in the unique way, H over U should be a solution of equation. But not to violate a condition of uniqueness, this operator, this field, a modified field, does not satisfy vertex condition. So here it means that in vertex, by differentiating, we create singularities and kind of put point sources here. And it means that we can express our new field, differentiated field, in terms of a combination of so-called edge-Green's function with some known coefficient. And edge-Green's function is just a solution of the original problem with one point source around some edge. And if we have like this type of angles, we should actually put more sources, but I don't want to get into these technical details. But anyway, what we have this expression for the solution. And this expression simplifies if we want to consider a far field. So if we want to study the directivity of the scattered field, we have a very simple algebraic expression. So the directivity of the field of the problem with a plane wave, OE, is expressed as a linear combination of directivities of edge-Green's function just divided by some polynomial. And to make things more apparent, I will give you an example for the problem of diffraction by a segment. So we have this finite segment, we have an incident wave, and to get an embedding formula, we need to consider two auxiliary problems. A problem with a point source here and a problem with a point source here. Of course, because of symmetry, we can express S2 in terms of S1 if we want. And then we apply this operator. By definition, this operator kills the incident wave, and it preserves boundary condition because we differentiate along the strip. And then we have this very nice, neat expression for the embedding. This is so-called very well-known embedding formula for the strip. And the nice thing about this formula is that before we had a function of two parameters, so we were depending on the angle of incident. But here we have a combination of two functions, but each one depends on one parameter. So if we found S2 and S1, we have the solution for all values of incident angle, which makes it very computationally efficient. And this is an example. So here is just an absolute value of directivity for the strip problem that we calculated directly. And we can build all these nice graphs from just one graph for the directivity of the edge-Green's function. So it's like a very powerful analytical relation. So now I want to talk about Wiener Hopf perspective on embedding and what we did with Anastasia regarding it. So I'm not sure how many of you are aware of Wiener Hopf or method in general, so I will give you a very brief introduction. A standard way to obtain a Wiener Hopf equation is to consider a problem of diffraction by a half plane. And just as it was shown by Wiener Hopf, this problem can be reduced to a convolutional or integral equation, and then this convolutional or integral equation can be reduced to the following functional problem. So here we have two unknown spectral functions which are Fourier transform on half lines. So here we have a Fourier transform of a normal derivative of a field And also we have additional Fourier transform here on the minus half line. And also we have so-called kernel. But the idea that we have a functional equation that has two unknowns, but still this equation can be solved because we have additional analyticity conditions on unknown functions. So this function U minus, because it's one-sided Fourier transform, it is by definition analytical or in the lower half plane of variable z. And this function I is analytic in the upper half plane of variable z. And also, additionally, which is also an important part, we have growth conditions for both functions. Both functions are basically decay at the infinity, and this condition follow from the behavior near the edge, which means we don't have singularities near the edge. We don't have point sources. We could have singularities, but we don't have point sources. And how to solve this equation? We need to do two procedures. First, we need to factorize the kernel, and then we need to factorize the free term. And what do I mean by factorize? We need to decompose the kernel into a combination of two functions, analytical or in the upper half plane and lower half plane. And in this case, it's quite easy to do. Here we have two square roots, which analytical in two half planes correspondingly. One can say why, but one can ask why. Why do we have this analyticity? But here we need to have in mind that we suppose that K have a small imaginary part, just to be formal. So we slightly deform K, move K, the wave number from the real line into the imaginary half spaces. And then as we solve a problem, we can consider a limit as K turns to zero. This thing is called the radiation principle in terms of absorption principle. And then we factorize the free term. And the free term is factorized basically by pole removal. So what do we have? We have this thing is 1 over k minus z multiplied by pole. And then we just subtract the pole, and you can just check this thing is analytical or in the lower half plane, and this thing is analytic in the upper half plane. And then finally, we can do the magic. We can apply Liouville theorem. And Liouville theorem says if a function analytic in the whole complex space, then it should be a polynomial. But since we know that both left-hand side and right-hand side turns to zero as we go to infinity, then it's zero. And we have the following solution. And what I want you to do is just notice that this solution has an embedding structure. Here we have this function should depend on two parameters because it's a spectrum of the scattered field. And here we have a combination of functions which depends on just one parameter and some polynomial, a very simple one here in the denominator. And we noticed this thing with Anastasia, and our question was like this: does it mean that that if we have a Wiener Hopf problem, then we have an embedding formula? And it turned out that the answer is positive, at least for the wave problems we considered. And we think we can derive the embedding formula like this for any wave problem. So generally, what we have? We consider a Wiener Hopf equation, a matrix one. So here it's like a general version of the previous equation. We have some polar forcing, and then what we do, we solve this equation n times, where n is the size of a matrix, and compose some so-called normal solution, x plus and x minus. And then from these solutions, we build a factorization of the kernel. And then we make a final step, a pole removal, and get generally a solution in this form, which we call an embedding formula from Wiener Hopf perspective. Of course, by default, we don't know these functions, but we can like formulate some diffraction problems for them. And here I want to go to some examples. One example, and before I will go into example, I want to introduce you a tool to derive Wiener Hopf equations very fast and in a very simple way. So what we have here, we have a green formula, and we apply this formula in the upper half space on this contour. And as r tends to infinity, we have only integrals along the real axis. And we apply this formula to a plane wave with some spectral function, which, as you can notice, related to the kernel of the previous Wiener Hopf equation. And the other function is a scattered field. And when we apply, we get some functional relation on a real line between spectrums of a scattered field. And then combining this functional relation, we can derive basically any matrix Wiener Hopf equation. And to demonstrate all this technique, I will consider like a more or less simple problem, but still kind of tricky, complicated one, a problem of diffraction by a right angle. So we have this problem, we have a Helmholtz equation, a Dirichlet boundary condition on a surface, and we have some Mechner condition, the way field behaves near the edge. And like usually, we want to find the directivity of the scattered field. And what I do here, I apply the reflection method, but only halfway. So I get rid of this boundary, and now I only have boundary data along the x-axis, and then I will be applying the Green's theorem 3 times and just getting a matrix Wiener Hopf equation. And so what I do, I apply a Green's theorem here, here. I have some unknowns with just either field or its normal derivative somewhere on the x-axis. And after some tiring algebra, I get the following matrix Wiener Hopf equation. So here I have 3 unknowns. This matrix, and some right-hand side. You can notice it mostly polar, but also I have this gamma, but still I can treat it almost as pole type of sourcing. And also, of course, this equation, this matrix is interesting by itself because we have 3 by 3 problem, and in general case, it's very hard to factorize 3 by 3 matrix problem. We don't know how to do it, but here it turns out that I can find a special transform which will reduce this to 2 by 2 matrix, and this 2 by 2 matrix is of Danieli-Hrabkov type. So this matrix can be factorized, but I'm not planning to do it here. I'm planning to demonstrate how I derive embedding formula. And to derive embedding formula, I consider 2 auxiliary problems, a homogeneous ones, or corresponding to some edge-Green's function. So here I have like 1-point source coming to the edge, and I consider some limiting procedure as epsilon goes to 0. And here I have 2-point sources. And then from the solution of these problems, I compose a normal solution. And this normal solution I use to derive an embedding formula. So I have an equation like this. I have some polynomial in the denominator. And I have two functions that depend only on one parameter. Of course, if I study it further, I can find a relation between this formula to the classical one. And I can relate the spectrums of the field with the directivities of the scattered field, and then I obtain a well-known embedding formula. So here, or it's coherent. But the main benefit I get is that I don't need to guess a differential operator. So I think, just not to bore you, I will skip this part. This is another way to approach wedge problem. But what I want to say, what we get from this perspective, we get a very algorithmic way to define these formulas. And one possible generalization is to consider a discrete diffraction problem, a problem on lattice, or we can think about these points as beams, some like lattice mechanical problem. So we have, as a simplest example, as I said, a finite difference approximation to the Laplace operator. And then we can actually build an analogy between this finite difference approximation and a continuous problem. We can derive a Green's formula with some analog of a normal derivative. And then using this formula, we can derive all the Wiener Hopf equation for these discrete lattice problems. So here I won't be going much into details, but the main idea is that we have Green's formula on lattices, and it allows us to do all the same stuff. And how this analysis, but now we need to operate. So now we will have a Wiener Hopf problem on a unit circle, and before we had a Wiener Hopf problem on a real axis. We will have some different expression for a plane wave, and instead of the infinite Fourier transform, we will have a discrete Fourier transform, and our square root gamma or epsilon here will be look different. And this is how the square root looks for the discrete problem. And for example, the simplest example, we can consider a problem of diffraction by a strip. It can be reduced to a matrix problem in the continuous case with this exponential growth, but in the discrete case we have just a polynomial growth, but a very similar matrix. And by analogy, we can derive an embedding formula for the lattice problem. It's very similar, but now it's just different functions. And of course, also we can derive this formula using a finite difference operator. So instead of differentiation, we apply some finite difference, for example, like this, and this operator will keep all the equation but kind of violates them in just 2 points. And then we can consider some additional edge Green's function problems for this lattice, and we will get an expression like this. That will work as embedding for the fields. The same way we can do the wedge problem, but in this case, it's just a bit more cumbersome. But still, we get some polynomial in the denominator. We get some functions that depends only on one variable. And also, we can do it using some second order finite difference operator. Also, we will have the same situation. It will preserve the equation everywhere, the equations, but violate them in just a couple of points, and then we will be able to express the field in terms of solution of couple auxiliary problems. So, and like an ultimate result for these lattices is that we can just obtain the embedding formula for an arbitrary shape, because here we just have a small wedges, and we can apply this formula to each wedge one by one. And what else we want to do here? The problem here is that if we consider an arbitrary polygon, and if some angles of this polygon are irrational, we don't have any embedding formula at all, because we cannot apply a method of reflections. And this problem is open, and we want to do something about the treatment of this special case. Also, another question is whether we can generalize all this research, all these results to 3D problems. The problem of diffraction by a quarter plane. So here we can formally start to act the same. We can derive a Wiener Hopf equation, but this equation will be 2D. And for this 2D Wiener Hopf equation, we actually cannot apply, we don't have a good analyticity regions for unknown functions. We know an analyticity region for one of them. This W, this function is defined on a quarter plane, and this is just analytical in a quarter half space. But this one is much more complicated, and we cannot say something simple about it, so we cannot give some simple factorization of K and found the solution. So all this algorithm doesn't work very well. But still, we think that there is something to do here. And what I want to advertise is a paper by Asier and Shakin, where they established so-called method of analytical continuation for this problem. We can treat this function as like known and analytically continue from the region of analyticity of initial function to the region of analyticity further, extending studying function step by step. But just to give you a bit of context, we can try to draw singularities of a function. And now the singularities, they are lines instead of points as they were before. So before we have just a pole or a branch point, but now we have lines, branch lines, and moreover, these lines could intersect. And the question, can we like study analytically those, very complex function, but comparing the problem with plane wave to the problem with the point source, and just by analytical continuation, say whether we can or can express one function in terms of another or don't. But this, of course, is future work, so I cannot say much about it right now. And okay, I think I will skip this one because it's too much. And what I can do, advertise our paper. So if you got interested in the topic, please you can read. It's available on Archive. Okay, I think that's all. Thank you for your attention.